Hello, thanks for coming to my presentation. Today we will be talking about using Dart FFI for compute-heavy tasks in Flutter apps. There were already some talks dedicated to FFI today, but mostly focusing on integration with other libraries and other APIs. And we'll focus instead on computation and on performance instead of using FFI just as an interface. But let's start with defining what Dart FFI is so that we're on the same page. FFI stands for Foreign Function Interface, and Dart FFI allows us to call any other language from Dart as long as this language exposes function in a C calling convention, which is a case for obviously C, but also pretty much any other language can be compiled into a form that is exposing such interface, and this way we can communicate between Dart and this language very, very efficiently. Also, via FFI, via C interface, we can allocate native memory, so using malloc, calloc, free, etc. Those methods known to many of us for manual memory management in the operating systems. There are a few use cases for FFI. First is the one that was covered today in some part. It's integrating with either existing libraries or integrating with platform APIs, so Android, iOS, etc. Of course, as I said, for libraries, we need to have C calling convention API available, but usually it's either available or can be made available via compilation flag, etc. Or in the worst case scenario, we need to wrap our library into our wrapper and expose this API that way. Regarding the platform native APIs, here is a bit of a caveat, at least for Android. The Android NDK, so the C++ APIs, are in some parts limited in comparison to Java and Kotlin APIs. So there are things that can be done in Java or Kotlin on Android, but cannot be done via NDK, and then we would need to use like JNI, Gen with Flutter to access those APIs. And the first use case, and the one that we'll be focusing during this talk, is implementing high-performance algorithm. So using FFI to access C, because C is a more performant language than Dart. But first, let's consider other options, because FFI, as we will talk, is not without its own drawbacks. So let's consider first if there isn't a simpler solution. And of course, first thing that comes to mind if we are talking performance is multi-threading. However, in Dart, multi-threading is limited. And even if our task can be multi-threaded, we can spread it into multiple separate tasks that can be executed by multiple threads. In Dart, there is additional problem in the way threads are made available to us, because we actually have access to isolates. And isolates, as the name suggests, is isolated. We do not have any shared memory between isolates in Dart. And that means that whenever we want to hand over some task to a separate thread, we need to copy data related to this task. And this is a very significant overhead, especially for tasks that require a large amount of input or output data, which makes multi-threading in Dart a lot less performant than it would be otherwise. There is technically a class that the name would suggest completely solves this issue. There is a transferable type data class in Dart that sounds very good because it lets us move data between isolates in constant time, which sounds perfect. However, creating this transferable type data object takes time proportional to the data size. So we are back in square one. Maybe we haven't copied the data, but still it took a lot of time. And to make the matter worse, it's not like this transferable type data can be used multiple times and we can just allocate it at the beginning and then use it throughout the app lifecycle. We need to create new instance for every transfer between isolates. Also, it's worth noting that every communication between isolates is done via ports, which is by definition asynchronous. So we will not be able to do any kind of synchronous communication. Of course, there are use cases where multi-threading in pure Dart with isolates does make sense, and those cases are we either have little amount of data that needs to be passed, and then we are making some kind of expensive computation, or the isolate can load this data on its own. So, for example, we want to decode, decode an image from disk, and we can load this image directly from the phone memory or fetch this over the network. The second option would be, instead of isolates, we could use platform channels. With platform channels, we get access to platform-specific languages and platform-specific tooling. So Java and Swift and Kotlin are slightly faster than Dart, and also are more mature ecosystems with more performance-related tooling. However, we have pretty much exactly the same problem as with isolates. Actually, it's exactly the same image, just with different labels. Again, we have absolutely no shared memory, so every communication requires making a copy of that data. Also, we have even more problems. First, we have platform-specific languages, so we need to implement this algorithm multiple times for every platform. Platform languages, Kotlin, Java, etc., are faster than Dart, but are not as fast as C, obviously. And same as with isolates, only asynchronous communication, no way around it. So, FFI. FFI, of course, is not a silver bullet, and it does require consideration whether it's worth using in this case. On the plus side, obviously, we get access to high-performance language such as C, C++, etc. But this performance isn't free. There are trade-offs, and the trade-offs are the reason for this performance. Actually, is that there is a lot fewer checks, and there is not as much safety net as we have in Dart. No null safety, obviously. We need to manually manage memory in many cases, which can lead to bugs simply. On the plus side, we also gain access to optimization techniques that are not available in Dart, although SIMD mentioned here is technically in part available in Dart, but it's very limited. Also, we have one implementation for Android and iOS and other platforms. However, while the operating system doesn't really matter in the case of C, other differences between devices may matter. So some architecture or processor features, such as Neon, the SIMD that we'll be using, is available only on ARM processors. So of course, if we compile it for Windows on x86, it won't be available, and we will need to implement two separate implementations: one for Neon, one for Neon with on ARM processors, and one for other APIs from different architecture. Of course, if we select C, we need to do manual memory management, and even if we use a different language that does help us with memory management, we will still need to manually manage memory that is exchanged between or reused between Dart and native code. Also, we are introducing additional language into our build process, which also complicates the build process. Okay, so let's see how much we can theoretically gain from the migration to C. This is a graph that Debian team is is preparing benchmarking different programming languages. It's sort of hard to read, but let's get through it. Dart is it's in two separate parts, and some parts are overlapping. Dart is here on the right side, and it's around 5 times slower than the benchmark. Benchmark is obviously C here, which is the fastest one in this measurement. Swift and Java is here. It's slightly faster than Dart, but it's, I don't know, 20% maybe. Okay, so we can now go to the how to actually use Dart FFI, and we'll start with pure Dart. We'll need two packages. First is coming from the Dart SDK, and it's Dart FFI package, and it provides us with native types, so pointer, struct, double, etc. We'll need those to define interfaces for our FFI functions, because of course types between Dart and native languages don't match. It gives us function to open and load our dynamic library during runtime, because we will need to do that, and look up functions from that library so that we can actually call them. Also, there is a currently experimental, also although quite mature, annotation at native, which allows us to bind external methods more automatically. I will show the example of how that works, and also it has a very important performance advantage. And there is a native finalizer, which is a callback that allows us to dispose some native resources. But sir, let's start with this native annotation. So we can more easily bind the native function to a function in Dart that we can actually call, but that's just convenience. But also, with native annotation, if function is a leaf function is a function that is supposed to be short-lived, and it cannot interact with Dart runtime, so we cannot call back from this function into Dart. And if those assumptions are true, one thing is that Dart can skip some additional checks during call, which makes it slightly more performant. But also, Dart allows us to access type data address. So we can allocate type data on a Dart heap and get address to that type data buffer in memory and pass it to FFI, which allows us to pass large amount of data from Dart to native code without any memory copy. The disadvantage of that is that Dart is unable to run certain tasks during this leaf call, so garbage collector won't run during a leaf call. But as long as it's quite quick, it's fine, and we can avoid copying data between native and Dart memory. Because otherwise, we need to first allocate our data on a native heap, and then we can pass it easily, but we can also access it from Dart. So the difference is that in one case, we need to keep our memory on the native side and access it from both languages. Here, we can keep the data on the Dart side, where it's memory managed, and access it also from the native side. There is the second nice feature of the FFI package is native finalizer, which allows us to attach a callback to a Dart object, which will be called when this object is garbage collected. So if we have some kind of resource on the native side that needs to be disposed, we can attach function that will dispose this native resource to a Dart class, and when this class is garbage collected, this resource on the native side will automatically be cleaned up. However, there are some caveats to that. And the fact is that while native finalizer is guaranteed to be called before the isolate is shut down, it's not guaranteed to be called in any specific time frame. So if we have some resources that should be cleaned up because they take a large amount of resources, we should still preferably dispose of them manually, especially that Dart garbage collector is not aware of the memory that we have allocated natively. So it won't know that it would be worth to run because we use a lot of native memory. Okay. Second package is the FFI, this time package from pub, and it gives us a couple of convenience methods, so malloc, calloc, and free, methods for allocating native memory, and methods for converting between Dart strings and native strings, because in the native world, string is just an array of characters with a terminator at the end. In the Dart world, it's obviously more complicated, so we need to convert between those two. Okay, let's go and quickly look at an example. So here we have the Dart Dart example. Oh, I can make it a bit bigger because you won't see anything. It's partially based on the official examples from Dart, so you can also reference those. We have a C library. We won't get into how it's compiled, and this library exposes few different functions. There is a reverse function which just reverses a string and returns it. There is a coordinate struct that stores coordinate, latitude and longitude. There is a function distance that calculates the distance between two coordinates. There is also a function to create a coordinate, although it's not strictly necessary. I'll get to it. And there is a function to add all the numbers in an array that was passed. And free bitmap function, it's just calls free, but I wanted to have some logging in this function, so we'll use it later. So how we access those functions on the Dart side? First, we are not using the native annotation, so the most manual way possible. We need to find the path to our library because depending on the platform, it may be slightly different. Then we load this library from this path, and using this library object that we have received, we are looking up those functions. During lookup, we need to obviously pass the name of the function that we want to find, but also we need to provide two type annotations. First is the native type annotation, which will be using those native types I've mentioned. So, for example, int32 and pointer UTF-8. This is string in the native world, in the Dart FFI world, maybe let's say. And we need to provide Dart signature. So here we will be using standard types like int, doubles, etc. But for strings, we still need to use pointers because strings are allocated on heap, and we need to more manually copy them between Dart and native memory. So with those values, we get function that we can call like any other function in Dart. For structs, we need to create a class which extends struct. There is just a few caveats. First, we cannot just allocate struct with the default constructor in Dart. It will throw an exception, I believe. We need to create it with this struct create method, and then we can assign values to it quite normally. Our field needs to be also marked as external and need to have native type annotations. We can obviously pass create struct. It doesn't really matter. We can pass structs to functions as any other types in Dart. Okay, and last but not least, the example of the native finalizer. So to attach a native finalizer to a class, we will define a native bitmap class. It's just a bitmap class that holds data on the native heap. So here we need to implement finalizable, and we need to have a native finalizer instance. It's critical that this instance is accessible during a specific instance of native bitmap being disposed. So that's why this finalizer is a static field, so that it has like life cycle of the whole program. And during creation of the bitmap, we are attaching this object and passing a pointer to the data that we will be disposing. And this finalizer, in turn, is calling the freeBitmap method on the native side and passes the pointer we have attached here to this free method, and it will in turn dispose of this memory. Of course, if we call dispose manually, we need to remove this finalizer to avoid freeing this memory twice and causing a crash. Okay, and how we actually use those functions. Here, let's start with the reverse function. We are defining our word that we want to reverse, and then we need to convert it to a native string using this toNative UTF-8 method. Then we can pass it to the reverse function, and again we'll get a native string in return. So we need to then convert it back to Dart string. And of course, we need to remember to free both our original native string and the native string that we have received from the function. Coordinate here we can creating using the constructor we've defined, or using a method, a function from the native side that returns a coordinate struct. And we can simply pass it to function as any other argument. I've skipped the native add native annotated function. So this is the other way, the more modern way of using FFI, and it's with this native annotation. Here we just need to mark our function as external, add this annotation that defines the native type and provides the name of the function. And we can call this function as normal. However, this requires using build hooks and code native assets in Dart, so that linker during compilation can link those functions together. And for that, in this example repository, we have a build hook that compiles our library and adds it to the source of our library. And when we call the add function, as you can see here, we are allocating a type data on the Dart side and filling it with values. And then here in the add function, we have access to this special address getter that returns a pointer to this type data. And this is only possible because this function is using native annotation and is a leaf call. Okay, can run this. Okay, it works. There is one more thing that I want to show you here, and it's that our native finalizer, here we are creating the native bitmap, and you can see that bitmap gets created, and then once we get out of this code block, this bitmap is no longer accessible. So garbage collector could clean up this bitmap and could remove the native the native memory. And this is currently happening. We are first freeing the bitmap data, and then we are getting to the end of the program. However, if we remove this loop here that stresses the heap, this will no longer be the case. First, we'll get to the program finished, end of the program, and only then, when the isolate is getting shut down, bitmap will be actually freed. Okay, going back to the presentation. How is the FFI in Flutter? We need to, or maybe we don't have to, but the best way is to create a FFI plugin, and we can do this with Flutter create command with template plugin FFI, and providing the platforms that we want to create. And this will do a few things for us. First up, it will set up the build process, and it will give us the boilerplate for loading library, and also will give us FFI gen configuration. We can now go here and actually create such a plugin and take a look at what has been created. First up, in SRC, we get example C implementation and a piece of CMake responsible for building this code. This CMake is also integrated with Gradle on the Android side, so that during Android compilation, our native code is also compiled and bundled together. On the iOS side, situation is similar. However, there is one more caveat. We have this weird additional file generated, which is only here because relative imports are not supported in Cocoa pods. So Cocoa pods includes this FFI plugin file, and this FFI plugin file includes our shared library implementation. And the C code on iOS is compiled with S code, exactly the same as any other Objective-C or Swift code would be. Also, we get a config for FFI gen. FFI gen is a package that generates bindings for us based on C headers. So, okay, it is generated. So we will have here already all the types and all the methods that are all of those native types have been defined, and all the methods have been resolved, and we just get access to a pretty nice interface of the C library under the hood. And here we get the boilerplate code for loading the dynamic library during runtime. If we are using the native annotation, we can define that in FFI gen, that we will be using FFI native, and also which methods are leaf calls, and this will cause FFI gen to generate bindings for us that are using the native annotation, and also are defining that those methods are leaf calls, so that we can pass those addresses, those pointers to type data. Okay, going back to the presentation. Real-world performance of FFI. We'll be looking at two examples. Both of them are coming from my side project, which is a pixel art graphics editor. So there are quite a few computer graphics algorithms that need to be pixel perfect and need to be fast still. Even though it's pixel art, it can be pretty large. So first one of them is alpha premultiplication. Alpha premultiplication is converting between two different types of image representation in memory. Basically, in some cases, we want red, green, and blue channels to be already multiplied by alpha by the opacity value, because it makes composing those images faster. And in Flutter case, premultiplied alpha is required for conversion to UI image object in Flutter. Here's the super simple implementation of premultiplication. We are going over all the pixels, getting RGB values, multiplying them by alpha, dividing by 255, and writing them back into the same array. Here is the optimized version, which doesn't use division or any other operations other than multiplication, addition, and bit shifting. And for performance, here actually we can already see some interesting results, because while on Android the optimized version in Dart is significantly faster because we've reduced time by 40%, on iOS we have lost performance. Actually, this seemingly much more optimal implementation is slower on iPhone. So it's a good example that we need to measure things because results are often different than we would expect. In terms of C, in C, the relation between optimized and non-optimized version is as we would expect, and we're reducing time by 45% on iPhone and 52% with optimized version, and 63% and 75% on Android. Although keep in mind that we are comparing here against the unoptimized. Here we are comparing against. No, we are comparing against the unoptimized version. So here the reduction is smaller on the Android side if we compare against the optimized. Flat fill. Flat fill, otherwise known as the bucket tool in MS Paint. On the left we have just illustration of the algorithm. On the right, this is the actual pattern that we'll be testing against. By the way, it's higher resolution than it's not a single pixel wide, but it's this long squiggly line. So it's pretty pessimistic case for flat fill. And here on iOS, we have reduction of 57% by moving from Dart to C, exactly the same algorithm, and 40% on Android. Now the interesting part, how fast we can actually make it if we try. So first, we can obviously try multi-threading, and here we have two versions on Android. First with transferable type data, and here across both platforms we are actually losing performance because the overhead of moving data between threads is more expensive than the performance gain that we are getting by using those multiple threads. FYI, we are using 4 threads in all those examples. And we have second versions from Dart, which is using native memory, because we can also use FFI tools to move data between threads. Right? We can allocate data on the native heap, and then we can access this data from both isolates. So FFI gives us sort of the shared memory that we always wanted to have in Dart threads. And with that, we actually gain performance, 39% on iOS, 52% on Android. And with FFI and multi-threading, we have 79% performance on iOS and 73% on Android. So we have finally achieved this 5 times performance gain that we wanted. But that's not the end. Next up, we can use SIMD that I've mentioned previously. SIMD is a feature of modern processors that allows us to compute multiple calculations on a single thread as long as it's identical computation. So premultiplying alpha is pretty much perfect example of using SIMD because we can compute 8 pixels at a time because we need to multiply every red value of every pixel by its alpha value. So we can calculate 8 pixels at a time. And with SIMD, we can SIMD only. We are reducing time on iOS by 91% and 83% on Android. But SIMD is single thread, so we can combine both SIMD and multi-threading and reduce the execution time on iOS by 95%. So 20 times, basically. On Android, we have lost a little performance by adding additional threads because we have already made computation on a single thread with SIMD so efficient that multi-threading actually costs us more the overhead even in C than we gain from multiple threads. Of course, with thread pool or some other solution, we could optimize this further and make it slightly faster, but I didn't went there. I have also tried GPU implementation with Metal on iOS. However, there are a few caveats. I have changed slightly the measuring, the way I measure the performance, so we shouldn't compare those results directly. And also, I haven't really optimized this Metal implementation, so it's only two times speed up. Yeah. Okay, so in the end, we have achieved over 20 times performance gain on iOS and 13 times 13 times faster than the fastest, so multi-threaded implementation in Dart. Okay. If you have any questions, feel free to ask them. Here are all the links to my Twitter, GitHub with the examples, and also the app. If you are interested checking out the editor, feel free.